Here's our equation. A and B are constants. And the question I'm asking, you can think of either of these two models or others. The question I'm asking is, under what circumstances can I make that same type of analysis into steady state and transient? Well, what does the solution look like? The solution looks like y equals a particular solution plus C1 y1 plus C2 y2. Therefore, to make that look like this, the C1 and C2 contain the initial conditions. This part does not. Therefore, if I want to say that the solutions look like a steady state solution plus something which dies away, which becomes less and less important as time goes on, what I'm really asking is, under what circumstances is this part guaranteed to go to 0? So the question is, when, in other words, under what conditions on the equation, A and B, in effect, is what we're asking, when does C1 y1 plus C2 y2 go to 0 as t goes to infinity, regardless of what C1 and 2 are, for all C1, C2. Now here there was no difficulty. We had the thing very explicitly, and you can see it. K is positive, this goes to 0, and if K is negative, it doesn't go to 0. It goes to infinity. Here I want to make the same kind of analysis, except it's just going to take it's a little more trouble, but the answer, when it finally comes out, is very beautiful. So when are all these guys going to go to 0? First of all, you might as well have the definition. So all the good things that this is going to imply. If this is so, in other words, if they all go to 0, everything in the complementary solution goes to 0, then the ODE is called stable. Some people call it asymptotically stable. I don't know what to call it. Yeah, I can make the analysis, and then I use the identical terminology, C1 y1 plus C2 y2. This is called the transient because it goes to 0. This is called the particular solution now that we labor so hard to get for the next 2 weeks is the important part. It's the steady state part. It's what lasts out to infinity after the other stuff has disappeared. So this is the steady state solution. Steady state solution, okay? And the differential equation is called stable. Now, it's of the highest interest to know when a differential equation is stable. A linear differential equation is stable in this sense. Because you have a control, you know what its solutions look like. You have some feeling for how it's behaving in the long term. If this is not so, each equation is a law unto itself and you don't know. So let's do the work. For the rest of the period, what I'd like to do is to find out what the conditions are which make this true. Those were the equations which we'll have a right to call stable. So when does this happen? And where is it going to happen? I don't know. I guess here. Now, I think the first step is fairly easy, and it'll give you a good review of what we've been doing up till now. So I'm simply going to make a case-by-case analysis. Don't worry, it won't take very long. What are the cases we've been studying? Well, what do the characteristic roots look like? The roots of the characteristic equation, in other words. Remember, there are cases. The first case is they're real, and distinct. R1 not equal to R2. Real and distinct. What are the other cases? Well, R1 equals R2. And then there's the case where they're complex. So I'll write it R equals A plus or minus BI. What do the solutions look like? So my ham-handed approach to this problem is going to be, in each case, I'll look at the solutions and first get the condition on the roots. So in other words, I'm not going to worry right away about the A and the B. I'm going instead to worry about expressing this condition of stability in terms of the characteristic roots. In fact, that's the only way in which many people know the conditions, though you're going to be smarter. Okay, what do the solutions look like? Well, they all look, the general solution looks like e to the R1t plus C2e to the R2t. Okay, so what's the stability condition? In other words, if the equation happened to have its characteristic roots real and distinct, under what circumstances would it be stable? Would it, in other words, all its solutions go to zero? So I'm talking about the homogeneous equation, the reduced equation, the associated homogeneous equation. Why? Because that's all that's involved in this. In other words, I'm no longer, when I write that, I'm no longer interested in the whole equation. All I'm interested in is the reduced equation, the part when you, the equation when you turn the f of t on the right-hand side into zero. So what's the stability condition? Well, let's write it out. Under what circumstances will all these guys go to zero? If R1 and R2 should be negative, can they be zero? No, because then it'll be a constant and it won't go to zero. How about this one? Well, in this one, it's C1 plus C2 times t multiplied by e to the R1t. Of course, both of these are the same. I'll just arbitrarily pick one of them. What happens to this as things go to zero? You know, well, this part's rising, at least if C2 is positive. This part is either helping or it's hindering. But I hope you know what these functions look like and you know which of them go to zero. They go to zero if R1 is negative. They might rise in the beginning, but after a while they lose their energy and go off. Of course, if R1 is equal to zero, what do these guys do? Linear, go to infinity. Well, we're doing okay. How about here? Well, here it's a little more complicated. The solutions look like e to the at times C1 cosine bt plus C2 sine bt. Now, this part is a pure oscillation. You know that. It might have a big amplitude, but whatever it does the same thing all the time. So whether this goes to zero depends entirely upon what that exponential is doing, and that exponential goes to zero if a is negative. So here the condition is a is negative. And now the only thing left to do is to say it nicely. I've got three cases, and I want to say them all in one breath. So the stability condition is, so the ODE is stable. So this is, or f of t, it doesn't matter. But psychologically, you can put this zero there. Is stable if what? If in case 1 this is true, if case 2 that's true, in case 3 that's true, but that's ugly. Make it beautiful. The beautiful way of saying it is if all the characteristic roots have negative real part. If the characteristic roots, the r's or the a plus or minus bi, have negative real part. That's the form in which, you know, the electrical engineers will nod their head, tell you, yeah, that's right. A negative real part, sorry. Isn't it right? Is that right here? Yeah. What's the real part of these guys? They themselves, because they're real. What's the real part of this? Yeah. The only case in which I really have to use real part is when I talk about the complex case, because A is the real, just the real part of the complex number. It's not the whole thing.